Hello, today I'm going to talk a bit about QuickSort algorithm, which is a very popular algorithm when it comes to sorting. It has much better complexity than bubble sort. Of course, it depends on nature of data, but the best performance of this algorithm in big O notation is is n log n, so it's quite effective. First, I will describe the basic idea of this algorithm. So in this algorithm we go after a branch and bound strategy. So what we are doing with our array with elements that we would like to sort is first we select our pivotal element, which will be used to reorder element around it. What it means? It means that if we select our pivotal element in this array, for example, somewhere in the middle, then we move all elements from the left side, which are higher than our pivot, to the right side, and every element which is on the right side and is lower than pivot element, we move to the left side. And after this, we again apply the same approach to the right side and to the left side arrays subsequently. So as you can see, probably we will have some recursion till we get our array sorted. All right, so now I will draw a very simple flowchart consisting of blocks essential for this algorithm. Those blocks can be implemented in different ways, so but I will try to explain the most popular one, the easiest one. All right, so first thing is what we have to ask ourselves: what parameters QuickSort will take. So this will be, of course, an array that we would like to sort, and the boundaries within which we want to sort elements. So our left side index and our right side index. Those left and right pointers at the very beginning points to the left points to the 0 index, right to the max index of the array. And we start from the decision block where we check whether our left index is not higher than right index. So this decision block is essential and will have an impact on when we stop our recursion. So if it is true, we are trying to find a pivot element. So this will be the element around which we would like to reorder order. So let's call this block find pivot. Find pivot. After we found the pivot, we call the next block, which we call partition. Yeah. So this method is very important because at this place we are reordering our array. After we reorder our array, so we have all elements less than pivot on the left side and all elements higher than pivot on the right side, we call again 2 times QuickSort. QuickSort for the left side and also QuickSort for the right side. So here's the recursion. We again call the same function. And then our algorithm ends. If this decision block is not true, we finish our recursion. Right? So here are the essential blocks. Finding pivot is very important because it has great impact on our algorithm performance. So of course the best performance is n log n. However, it might be a bit worse if we choose our pivot element wrongly. So there are many approaches on how to select pivotal elements. There are some approaches where we try to examine the nature of data and according to it select the pivot. For our purposes, let's say we will choose it somewhere in the middle. And the next important function is partitioning, as I said, where we're trying to reorder our array around pivot. And next are two calls to QuickSort function again, when we try to call the same approach for the left part and for the right part of the array. All right, so now let's go to the partition method, which is very, very interesting, and I will show you how it might be implemented. All right, let us use following array as an example for partitioning. As I said before, we will select our pivotal element somewhere in the middle. This will be our strategy of selecting pivot element. Let's mark it. So 5 is our pivot element, so we will be moving every element which are lower than 5 and exist on the right side of this array to the left side, and each element which is higher than 5 and exists on the left side of the array, we will move to the right side. So for that purpose, we will create two pointers, right side pointer and left side pointer. And the strategy will be as following. We will be moving left pointer and right pointer and apply swapping if we come across elements on the left side which are higher than 5 and to the right side if we come across elements which are lower than 5. So let's start. On the left side we are at 3, which is less than 5, so we can continue and we move our pointer to the 6. Now we are at 6. 6 is higher than 5, so it should be on the right side of the pointer. So we stop at this element and we mark 6 as a subject of swapping. Alright, we are on the right side. The left index is at 2, so and 2 is less than 5, so it should be moved to the left side of the array. So we don't move backward our pointer, we just stay here. So from this moment we can do the swapping. So let's rewrite our array after swapping those elements, 2 with 6 with 2. So we have 3, 2 goes to the left side, here will be 2, here will be 2 again, 5 our pivot element, 8, 1, 7 and 6. Yeah? Okay, let's rewrite our pointers. So our left pointer is here, our right pointer is here, our pivot is here. So we continue. After we continue, we move our left pointer to the right. So we go from here to here and see that 2 is less than 5, so we can continue. And we end up with our left pointer, which is at 5, which is also our pivotal element. We cannot go any further. Okay, on the right side we are at 6, we move to the 7, which is higher than 5, which is okay. Then we go to the 1, which is less than 5 and should be moved to the left side. So our right pointer is here and left pointer points to pivotal element. So we just have to swap those elements. So what we are doing now, we are rewriting again our array. We swapped 5 with 1. So we have 1 here, 8 here, 5 here, 7 and 6. So we can see our array is getting sorted. Again, we mark our left pointer, which is currently at 1. We mark our pivot element, which is at 5. The essential thing is that our pivotal element changed its position. So if we are in a partition method, we have to return this new position of pivot to the outside. So we can call QuickSort again with proper left and right boundary wires. All right. So and on our right side we are here. So if we are here on 5, we can't move forward because our right pointer points to the pivotal element. Yeah, but we can move our left pointer. We are going to the next element, which is 8, and 8 will be a subject of swapping with the right pointer, which points to the pivotal element. So it will be our last swap. Then we get 2, 2, 3, 2, 2, 1, 5 after swap, 8, 7 and 6. So as you can see, our array got partitioned around pivot. So on the left side we have all the elements which are less than 5, and on the right side we have all elements which are higher than 5. Okay, this partition. So after we return from the partition part, we will apply the same approach to this array and to this array. Yeah, and as I said before, we will finish this this recursion after we find that our left and right pointers are equal. Yeah, or when our left pointer and will be higher than the right pointer, then we stop recursion and we can assume that our array got sorted. Okay. So of course, to better understand this approach, it's good to see some implementation. As usual, you can find on my GitHub repository, which I put the link below. So then you can find my implementation of this algorithm in Java along with Spoke unit tests.